Welcome back, everybody. We're taking a look at section 4 of Unit 10, the gas laws, and this section is about real gases. Now, here's the deal. We've been talking about ideal gases and using that phrase all along, and we're saying ideally, these gases have no affinity to one another. They keep on moving around, and the reality is there are some conditions in where the gases, we've got to factor in some other factors, and this is more of a physics thing that goes with it. The reality is that real gases do exist. They take up the actual volume that's used for movement rather than ideally take up the entire container. The actual free volume is going to be a little bit less than what we would say in ideal gases. Okay, they kind of stick together. And another thing that we need to factor in with that is we've been saying all along, kind of assuming that they just add up the pressures, but in reality, with real gases, and this is talking about really, really super low temperatures and extremely high pressures, they tend to stick or clump together. Okay, so the pressure of these, because of the attractive forces, the pressure in the container tends to be a little bit less in a real gas than ideal gas. Okay, so it's going to be a small difference in there, and so we can actually do some corrections for this. The amount of material will affect the volume. Obviously, add more things in there. There's going to be more sticking. The more moles, the more effect. And there is a factor or a constant that will differ for each gas. It's already been calculated out for you. So what we do also with the pressure is the same thing, and that A value will be a constant that differs for that gas. Okay, so we're just plugging in those values, and since the two molecules will interact, the effect must be squared. Okay, so it's just straightforward, and we're going to be comparing that to ideal gases. Says we're not going to worry about any of that. We're just going to say that they do this, but the real gas law actually takes into account those different variables about the volume of the gas being a little bit different, as well as the pressure being a little bit different. So what we see with the real gas law, otherwise known as the van der Waals equation, is going to be taking a look at those factors. Now, remember that your A value and your B value that was given before, those are going to be experimentally determined. So those are going to be variables that are given to you, and it's going to depend on a whole bunch of things. And once you see all those things, don't worry, don't stress about it too much. It just takes a little bit of discipline to track things, and the van der Waals equation is pretty easy to use with that. So you just kind of plug and chug those in there. Let's take a look at how this works in an application within the problems. Okay, so here, let me take a look at the problem since I didn't type it in. The problem we'll be seeing here would be, let's go ahead and do that right here. When I see the equation in here, we're going to be adding in this. All right, we see, let's see, find the pressure exerted by 0.5000 moles of N2 in a 1.0000 liter container at 25 degrees Celsius. So let's use the ideal gas law first, okay? Ideal gas law, let's just take a look at how this compares. If I was using the ideal gas law, we'd simply say Pivnert, so PV, my container is 1, and I have 0.5 moles and 0.08206, and my temperature is 298. So if it was up to my ideal gas law, I'd see that I have 12.23 atmospheres, okay? Once again, this is my ideal. Okay, now let's take a look at it and refer to it as a real gas. Okay, so we're going to use the van der Waals equation. The van der Waals equation. Okay, and so to do that, I see that my equation is P plus the 1.39 times my 0.5, that's my moles, over 1 squared. Okay, because that's going to be the size of my container. And this is also squared. Okay, now I'm going to take that times the size of my container, which is 1 liter, minus the 0.5 times a 0.039. This 0.039 would be given to me. Okay, and this will equal now my 12.23. Okay, that's where this comes in. All right, so if I'm going to derive this down, I'm going to get pressure plus 0.348 times 0.9805. That will equal 12.23. Well, if I take a look at this and solve for my pressure, okay, so I've got to multiply this and multiply this. So I take and divide, and I divide by my 0.9805. I'm going to get my pressure as now being a 12.13. That's my van der Waals pressure. That's my real gas pressure. Notice that my ideal was a little bit different. So the question is, how much is my percent error between my ideal and my real? Okay, so my difference, if I'm going to solve for my percent error there, I take my pressure of my van der Waals and the pressure of my ideal. I'm going to take the absolute value of that, and I'm going to divide it by my ideal times 100%. And so that will give me 12.13 minus a 12.23 divided by my 12.23 times 100%. That will give me a 0.82% error. Okay, so it's not that much of a difference in there, but there is a slight difference between our real gas value compared to my my ideal gas value. Let's take a look at another example of that, and let's say we have, well, let's just go ahead and say we have 0.5 moles again of my nitrogen, but this time we have it in a 10-liter container. And we're going to do that at, once again, 25 degrees Celsius. Okay. The reason that temperature is important is because that's my B value that I'm going to be using up. So if I'm going to be using my ideal and I want to solve for ideal, that's going to end up being my PV equals nRT. So my P times 10 liters, that's going to be a 0.5 moles, 0.08206, and my temperature is 298. So if it's going to be up to my my ideal gas, my pressure is going to be 1.223 atmospheres. Now again, this is my ideal. But if I was going to be doing the van der Waals or the real gas calculation, it gets a little bit trickier. So I see my pressure is a function of 1.39 times 0.5. That's going to be squared over my size of my container, which is 10 squared. Okay, again, my 1.39 is a value that's provided for me, okay, from the table. Now, I'm going to multiply that by my size of my container minus the number of moles times my B value. So that's going to be also supplied for me. Okay, that will equal 12.23. Okay, the reason I got this 12.23 is this is 12.23 here. Okay, that's my that's this side, that's the nRT value, isn't it? So this is my nRT. That's where that 12.23 came from. Okay, so multiplying this all out, squaring it and squaring this and dividing, I end up with my P plus, let's see here, 0.003475. Okay, so that's this, square this, divide, and add it to my P. And we're going to multiply that by this subtracted from this. So those two is 9.9805. That will equal my nRT, which was 12.23. Okay, so deriving this, multiply, then divide it over, I'll end up with 9.9805p. That will equal 12.195317776. What I did is I multiplied here, then I divided by, or sorry, I subtracted from the 12.23. Okay, so my P value now, if I divide, I'll end up with a P equals 1.222. Now that's going to be the pressure on my van der Waals. Okay, and this is going to be in that's going to be in atmospheres. That's my van der Waals pressure. Now, if I wanted to know my percent error, okay, so my percent error is going to be my van der Waals. Okay, I'm going to take the absolute value, 1.222, minus my ideal, which is 1.223, divided by my my larger number, 1.223, times 100%. Okay, so I'll end up with a 0.082% error. Larger container, the less they tend to stick together. There's going to be less pressure in there, and so they're not going to be as sticky. If I made this container smaller, then all of a sudden I create more real gas air in there. Okay, that's all we need to do, guys. Just keep track of the van der Waals and the values, and remember, this value is going to be provided in the table. This value is going to be provided in the table, and when I set that equal, that's going to be the nRT side. Okay, we don't bring over the volume side with that. So that's where those values come in, and I think you'll be able to do some of the equations. They go slow with it, and you should be fine. All right, good luck.